Today we're going to work on the review, so everybody get out your review and turn to problem number 3. We're going to work on this one down here because it's a ramp problem. I'm going to work 3 and then I'm going to work the one on the back, which is number 7, I believe. Yeah, so we're going to work 3 then 7 because they're both ramps, and then we're going to come back and we'll work number 4. So let's start with these. Now on inclined planes there's several ways you can do it, so I'm going to talk about both of them, but first you want to do is draw your free body diagram. So we know we have force normal, or we have force weight pushing down the weight of the block, and of course force weight always goes straight down towards the center of the earth. Force normal is always perpendicular with the surface, so there's force normal. It says it is sliding down and it has a coefficient of friction. So we know we have force friction, but we don't have force applied. So what I'm going to do is I'm going to move this over here and redraw it off the ramp. So we have force normal, we have force weight, that's probably a little bit off, force normal, force weight, and force friction. Now this one is on the y-axis. If I drew an xy axis, it would be on the y-axis. So if I draw an xy axis, neither of these are, and we don't really know their angles. We could figure them out, but it takes some geometry. But how about if we go back and we'll say, well, let's make this our x-axis and let's make this our y-axis. So this will be our y and this will be our x. Now I'm just going to rotate it just like we're used to seeing. We always see the x-axis going this way. So I will have the block and I will have force friction, force normal, which is normally what we see, and when I rotate it, force weight comes out this way. The only one that is not on the xy axis now, this is the x-axis and this is the y-axis, is force weight. And it's this angle. All we need to know is that angle. Turns out this angle is the same as that angle. It's 20 degrees. Okay, now let me show you another way. Some people see this better. I say lay the ramp down. Just rotate everything. So take this ramp and just rotate it. Just smush it. Lay it down. How many degrees did you lay it down? 20. Didn't you lay it down 20? So if you do that, you have basically what I was just saying. Force friction, force normal, and that makes, when you lay this down, look at force weight. Look what happens. You lay this down, doesn't he swing out this way? So force weight is like this. And we laid it down 20 degrees. So this is our free body diagram. Once we've got that, then we can start filling in. So I'm going to get a new sheet of paper here to do it on. So I have my free body diagram, force friction, and we know force friction is mu, and we happen to have a mu of 0.21 Fn. Force normal, force weight, and how do you get force weight? It would be mass okay, so now I have it labeled. This would be force weight something, and this would be force weight something. This is force weight in the x. That's the x component of this hypotenuse or this resultant. This is force weight y. Okay, now here's a problem. I want us to go back and remember sine and cosine. Remember, we have r sine and r cosine equals the x and y components. Well, it's flipped on this one. This is not a standard angle, and every once in a while it flips. I told you about 95% of the time it's going to be cosine for the x, sine for the y. But let's look at it. The side you want to know is opposite. Isn't sine opposite hypotenuse? So the side you want to know is opposite, and you got the hypotenuse. So it is sine this time. So this is force weight x, and this one's going to be force weight y. So I'm going to go ahead and write in the values here. So force weight x, force weight y would be r cosine theta. For the y, r sine theta. So this turns out to be 251.64. And this turns out to be, remember it's going in a negative direction, don't forget that, negative 691.4. I now have my free body diagram completely labeled, and now I can continue on with the problem. Just like when we did in projectiles, you can't add your x's and your y's, so we need to talk about them separately. Now we know that this block is moving down the ramp, so we have to assume it's accelerating. So we know that the sum of the forces, total forces, net total, however you want to call it, has to equal mass times acceleration. Okay, which way is it accelerating? Is it accelerating in the x or the y? Now remember, we moved our ramp. This is the direction it was accelerating in the original picture. But we laid the ramp down. Now this is the direction. So it is accelerating in the x. So I can say if you add up all the forces in the x, they will equal mass times acceleration. What will all the forces in the y equal? Remember, this little symbol in math means sum, the sum of. So I can say acceleration equals, who are my forces in the x? I have force weight x minus force friction. Okay, I'm going to rearrange it, divide it by mass, so it turns out to be this. 75 kilograms is the mass. Force weight x, 251. And force friction, mu Fn, which I calculated, well, I don't have Fn yet. Okay, they want us to find acceleration, I guess. Yeah. Oh, they just said draw and label the free body diagram, but I want you to figure out acceleration. Okay. This is one of those, oh dadgummit, if I only had Fn. Where am I going to find Fn? What kind of force is he? He's a force in the y. So I come over here, well, who are all my forces in the y? I have force normal minus force weight y. And we know force weight y is minus 691.4. That minus takes care of that one. So can I say 691.4 equals force normal? I take that and plug it in here, and I calculate acceleration.